Okay, and if you have questions that aren't reflected in the poll, you can raise your hand and then I'll take your questions. But let me try to take some of these questions first and then we'll see how that goes, okay? All right, so to get to this part, let's go to the next deck. Come on, I'm gonna fill this out. Okay, and go here. Okay, and hope that the pen also works on this deck. Okay, let's see. Oh, yes, it does. Okay, good. So what we were saying about the inductive bias part, right? Okay, I'm sorry, some of the coursemology questions, I think wrote inductive hypothesis instead of inductive bias. So we'll try to get that corrected. Okay, the idea, as I had expressed earlier, is the whole idea that, you know, when we have a learner, right, we want to be able to express whatever concept that we think we're trying to learn, okay? Now, because the entire set of possible hypotheses that are out there is enormous, right? It's basically the power set of all possible data values, right? So we have this script X, it says basically, what are all the possible observable data instances, right? Script Y would be, again, all of the possible observable class labels, right? So if I look at all of these, right, let's say I have two attributes, right? Let's say, can I write here? Yeah, F1 and F2, okay, feature 1 and feature 2, but maybe, let's see, let me try to write that in a different way. Okay, no. Okay, okay, X1 and X2, and let's say I have two values, okay, either a positive or a negative, right? So I have a positive, 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 negative, negative, positive, negative, negative. And let's say they're just Boolean attributes, right? So what possible hypothesis could be out there, right? Well, one is obviously, you know, I like all of these things. No matter what type of X1 and X2 you give me, I'm okay with it. So these are all positive values. So my Y value would be plus, 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 right? But there's also the possibility that, you know, I don't like any of them, right? Negative, 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 negative. And so there are basically, if you look at all four of these rows, right? How many different ways of constructing a function from this, right? So there are four rows, each row can take two values and the Y can take two values, right? So it's gonna be 4, oops, okay, the power set, right? Basically 2 to 2 to 4, okay? Basically how many different ways of constructing a labeling of these four rows, right? So that's why it's going to be pretty difficult. Okay, so let me erase all that. Okay. All right, so it wants me to erase this too, okay. So that's why we have this power set, okay? So there's so many different combinations that we can enumerate for a particular very large already set of data values, right? Basically all of the different rows of X that can exist and then the power set of labels there, right? So it's not really feasible even in this very limited space to say what concepts can I represent. So I'm going to use some type of a priori knowledge to encode what I think is a feasible set of hypotheses. Okay, that's all I mean. All right, so I'm going to consider different ways of constructing a hypothesis for that. When I talked about the conjunctive learner, you saw what it meant. It just meant for each of the hypothesis, I can only have a conjunction of different values for features. That's it. Okay, so I can't represent disjunctions. I can't represent anything more intricate than that. Okay, and as we saw, this shrinks dramatically the space of things that it can represent. But we think that's sort of correlated. You know, it's not a bad idea to just think of drinks having this conjunctive space. Okay. All right. So if we don't have a unbiased learner, if we have rather this unbiased learner rather than a biased one, right, then we will have this problem. We won't be able to classify new unobserved instances because for each one of these, it could take a different example. Again, it could take exactly half of the remaining hypotheses that are not eliminated yet, okay, that are not ruled out by examples in the data, would say yes to that example, and another half would say no. Okay, so basically this inductive bias is basically what we said here, just the minimal number of assertions that is going to allow us to come up with a target concept so that it has this entailment, right? Okay, let's see, can we move this over a little bit? Okay, well, I'm not very good at operating this. Okay, let's see. Okay, so that's the general idea. Without this inductive bias, we won't be able to generalize. Okay, so with the inductive bias of the candidate elimination algorithm, basically we are saying, you know, from the version spaces, right, we are going to be able to only classify instances that are unanimously declared positive or negative, right? If there's in the version space, okay, like we saw in a couple of slides earlier, something like here, okay, where some of these hypotheses say yes, and some of these other ones say no, then you have incomplete, well, you can't make a decision based on that directly, right? You can use a probabilistic assumption, but for the purposes of coming up with a proof for showing the inductive bias, we don't have a way of answering that, okay? Okay, so we need it to come up with the same thing as for all of the possible hypothesis inside of the version space, okay? All right, so hopefully that answers this question over here, okay? But if it doesn't, you can ask again and I'll try to address that, okay? Let's go on to the next question. Let's see. Okay, so let me make this side bigger for a second. Okay, that didn't work. Okay. Present again and see what it works out. Okay, yeah. So will the specific set always contain just a single hypothesis? Okay, if you're using FindS, yes, right? Because FindS is only looking for a single hypothesis. It's basically a greedy search, right? To try to find a single hypothesis that covers all of the specific positive examples and admitting nothing else, right? That's the whole idea of FindS. Okay, for the case of a candidate elimination, all right, will the specific set always contain just a single hypothesis? I think the answer is again yes here. Okay, we know that in the general case for the general boundary, we can have more than one, but the specific set can contain just a specific hypothesis. Okay, so when you have different training examples, the same training examples in a different order, you may end up with a different maximally specific hypothesis. You're going a different way in the lattice, and that can lead you to a different specific hypothesis. Okay, so that is the ordering of the data set also matters in the search for what specific hypotheses are coming out. Okay, so it is a deterministic algorithm, so it is influenced by the order of instances appearing with the algorithm. Okay. All right, okay, so far so good. So in the lecture notes, it says that the learner is biased due to inductive bias. However, in the pre-quiz, it says the learner is biased due to the presence. I can't read the rest of this, so let's see how I can get that. So I'm gonna take it out of presentation mode for a second. Okay, and I think I have to edit, let's see. Then I can see the responses. Okay, give me a second here. I did see it before. Nope. Let's expand this so I can see all the questions. Sorry about that. I'm still learning a lot of edtech technology in order to get things to work. Not this one, sorry. Right. Okay, how come I still can't? I want to see the, okay. I've got to figure out how to deal with this better. Okay, let me hide the ones that are already hopefully finished. So I can't read the rest of this. I have to figure out what it says. So if you are willing to air it in chat, let me just check whether chat is enabled. Then you can share it with me, or maybe raise your hand. I'll be able to see that. Okay. So the learner is biased, right? Because we needed to have some a priori assumptions in order for us to learn, right? So in the pre-quiz, it says that the learner is biased due to the presence of something. So we'll go to the coursemology site. Let's see what I can figure out where that is. Okay. Okay. Was it in the pre or the post? Let me see what you wrote. Okay, in the pre. Okay, so let's take a look at this question. Okay, so it says the learner is biased due to the presence of inductive hypotheses. Again, this should be inductive bias, right? So that's what we mean there. Hopefully that is the only thing that we need to clarify. Okay, that this was the wrong word. It's not inductive hypotheses, right? Okay. So I'm going to finish that one. Can you give an example? Okay, I'll come back to this in a minute. Okay, we'll just leave that there. Okay, I can do that. All right. Counting semantically distinct hypotheses. Okay, so semantically distinct means that, basically the expression of that hypothesis admits the same underlying examples, okay? It represents the same concept, right? So it means that the items that are positive and negative are within the same space, right? That they are given the same values of positive or negative. Okay, so how do we count them? Again, we had the slide to show you how to do that, right? Basically, we would take away all of the cases of if there are any the null value, right? Then that would lead to only one plausible hypothesis, which is rejection of everything, right? Then everything else could be counted, right? So if you have in conjunctive learning, we said that we would count all of the cases where we have a don't care, which would allow, as many values are in that feature, as well as the don't care example. So if there are 4 distinct attribute values, then you would have a total of 5 for that slot, right? And you would multiply this through all of the different features that you have for a particular data set. Okay, so that's how you count semantically distinct hypotheses. Okay. All right, so hopefully that covered that. Could you explain why the hypothesis space is the power set of input space for unbiased learner? So I think I covered that, but if you are not sure about that, I can cover it again, okay? Basically to say that we can enumerate all of the possible values in X, right? Our script X. And I gave the example of having a Boolean two attribute problem, right? You have an x1 and an x2, and they both take Boolean values, so they can take yes or no, or positive and negative, right? So in this case, we have 4 rows, right? Yes, 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 no, no, yes, and no, no, right? And for these 4 rows, any target function will have to label all 4 of those rows, right? So how many ways can we label those 4 rows? It's basically the power set of the size of x, right? So, one would be to label all of them as negative, one would be to label all of them positive. And so you can build this up, right? So again, I'll try to draw it. So let me go back to the PowerPoint and just get another slide here. Okay. Get another slide. Okay. Okay, so the idea is that you would have, let me get rid of these things. Can I get rid of them or not? Okay, then you would have an x1, an x2, and a y value, right? So you have x1, x2. Okay, and just looking at the first row, okay, how many ways can I label that, right? I could either label it plus or minus, right? If I have a Boolean output, right? And for each of these, then the next row, I can also label as plus or minus, right? So far, if I just consider these 2 data examples, I have already 4 different ways of constructing a concept, right? Either the target function prefers both of these examples, the plus plus and the plus minus, or this prefers both or prefers only one of them, right? And you can see how every time I'm adding a row, okay, I'm getting another exponent, right? Another multiple of 2 out of this, okay? So that's where we're going with that, okay? So this is basically the way we construct the power set, okay? So that actually worked pretty well, okay? Okay, am I right to say that the disjunctive hypothesis set cannot be represented in the hypothesis space? Okay, this is a trick question, right? Because the problem here is we need to know what type of learner we're talking about. If we are taking the assumption that we are using a conjunctive learner, okay, that our a priori bias, our inductive bias is that all of the targets that we want to represent, okay, meaning that we think the target concept that we're trying to learn is within the space of conjunctive concepts, then you are right, right? Because we took this assumption that our algorithm, that our concept is a conjunctive concept, right? So then we wouldn't be able to actually learn a disjunctive hypothesis, okay? Unless that's disjunctive is only a disjunction of one attribute, right? Then it's the same as a conjunction of one attribute. So yes, this would be the case when we are saying that we are using a conjunctive learner, okay? So when we talk about concept learning in general, we are not saying anything specific. For the purposes of the lecture, we needed it to be more specific. We wanted to illustrate that through the concept of using a conjunctive learner for concept learning. Now, of course, that also means that you don't need to use this. You can use a disjunctive learner. And in fact, some of the midterms that we've featured in the past make this hypothesis. Let's pretend we have a different class of learner than the conjunctive one that you studied, okay? Then if we permute the algorithm in a certain way, how does it work? Okay, so you can do this thought process on your own, and then or with your TAs in tutorial, and they can hopefully answer some of these questions as well. Okay. Okay, so we've done that. Okay. Confused about candidate elimination? Okay, of input instance if the vote among hypothesis of script HDF, thanks for putting all in the math there, is unanimous. Oh, here's how we do it. Okay, or not if otherwise. So yeah, I think this was also asked on the forum. So thank you for bringing it up here again. So when this is going to be the case, then we can say that the candidate elimination algorithm and the fineness algorithm will concur, right? Because obviously the fineness hypothesis will be inside of the candidate elimination output, right? The candidate elimination algorithm is basically generating a larger version space, right? It's giving you not just one hypothesis, but all set of hypotheses that are consistent with what is shown in the data set. Again, I think Eugene also mentioned this because some of you were a little bit confused. Consistency has to do with the concept with respect to the data set that's presented. Okay, the underlying target concept is represented only partially, right, by the data instances that the algorithm gets to see. There might be thousands of other drinks that the learner might want to drink or have in mind, but you only get to see this limited amount of data, right? If you look at this week's lecture, you saw the Enjoy Sport data set, which has 2 weeks of weather data. Of course, there are many more other days that we could decide whether to play golf or not, okay? The whole point is like when we have a data set and we can look at how the hypothesis that we have, whether it is able to establish the same values as the real values coming from the target concept on those particular examples, then we can decide whether it's consistent or satisfiable. Okay, but we can't say this overall, right? When we say consistency, we mean basically accuracy on the training data, right? Whether we get the same output on the training instances as what we got access to when we were learning the concepts, okay? So hopefully that answers this question, okay? Okay, so when we consider just the semantically distinct hypotheses, are we making some assumption, or does this suggest that the learner is biased? Okay, let me put this up. Okay, I don't think, oops, did I hide it? Drat. Okay, no, I hit the wrong button. I'm very sorry about that. So I think when we are trying to enumerate all of the semantically distinct hypotheses, we are talking about a specific hypothesis, a specific learner, which is making some a priori assumptions, right? So we're not saying anything when we enumerate the concepts. It's just that when we decide we are using a specific instance of a concept learner, whether it's a conjunctive learner or a disjunctive learner, then we are making specific assumptions, right? So we are putting this inductive bias into work, right? So the actual action of enumerating all of those values has nothing to do with the inductive bias or not. It's just conceptually when we decide which type of inductive bias we're going to use, then we are enforcing this prior, okay? Okay, so I'm gonna take this last one and then I'll answer a couple questions about projects, okay? Because I get a couple of you asking about that. So if you have more questions about that, I will take those and then I'll take about a 5-minute break to get some water and then I'll come back and answer the rest of the questions, okay? All right, so let's answer this one. Make sure I hit the right button. Why can we assume, since the target concept can be represented as a conjunction of constraints on the input attributes, we can classify unseen input instances? Okay, we can't assume that actually. We can only assume this when the target concept is actually represented by a conjunction of constraints and we are using a conjunctive learner. These two things have to be aligned together, right? If our target concept falls out of the box of what our learner can learn, can represent rather, then we're out of luck. You know, we can get our best approximation to it, but it won't be the target concept itself, Okay, of course, even if it's not the target concept itself, it may do very well, right? If we have certain data examples for our training, we still might be able to get all of the training examples, right? Because, again, D is not exhaustive of the entire space of X as possibilities, right? So we still might be able to get all of the items right in our training, but we're still not representing the target concept properly. We can only say we're representing the target concept properly with respect to the training data, right? So when we get some other data from testing, even if it comes from the same distribution, maybe we're unlucky. You know, we actually end up needing a different model representation, right? A different type of biases in order to correctly model what is in the target function. Okay, so there's two things here, right? There's the point that the target concept can be represented as a conjunction of constraints. That's one part, right? The other part is that we're using a conjunctive learner, right? If we're not using a conjunctive learner, even if we have the target concept being in this conjunction of constraints, because the two don't overlap or partially overlap, then we are not guaranteed to be able to say we can classify unseen instances correctly, okay? So most learners, as you'll see, they cannot refuse to give a output, right? So only in the case of trying to make a proof here and look at understand the ideas of consistency and satisfiability, we are allowing our concept learners basically to say, oh, I'm not going to say anything about this instance. I don't know what it is, okay? So that's why in the lecture notes it says, if there's a conflict in the version space, then we're basically saying, sorry, I'm not going to classify anything, okay? So I hope that clears up some of your doubts on that. Okay, can I give you an example of a project where total beginners made that is enough for an A? Okay, I really appreciate this question because it's very important, okay? It's not important to do any type of fancy machine learning or use deep learning and like that. It's just that it happens that a lot of our students tend to like those topics. This is why in our poll, we've shown these categories, okay? You can very much do a simple machine learning project, and as long as you're illustrating the understanding of the machine learning concepts that we are discussing. For example, later in week 5 and 6, we're going to go through very key concepts of bias variance, regularization, and validation. These concepts will help you understand what a learner is doing, okay? And so when we get an A project, it's not the performance that matters of your machine learner. It's not the complicated math that matters, okay? It's your understanding of why the results of your machine learning experiments are as they are, okay? So for example, I could try a naive Bayes learner, okay? And my hypothesis, okay, not talking about hypothesis based and et cetera, okay? In terms of scientific method, okay? I would say, if my hypothesis is that the naive Bayes will do poorly, okay, because it makes this very strong naive assumption about the independence of features, and I do a feature analysis to show you that, in fact, a lot of the features in this data set are highly correlated, okay, and then that predicts, right, why a naive Bayes system won't do as well. Okay, so that type of analysis is really critical because we don't want you to be running, code or coding up your own machine learning algorithms without the understanding about why the results occur as they are. Okay, so later when you learn regularization and validation, there are many ways to set those parameters. Okay, so when you set them, again, for the basis of your machine learning project, what we need you to do is understand what should be the expected results. Can you validate that the results that you see are in line with your expectation? Okay. And if they're not in expectation, we expect you to delve a little deeper to explain why. Okay. So like I said in the earlier one last week, anyone can run machine learning code. It's basically a push button facility. You guys have done it yourself in Collab. That's not our goal, right? The goal here is for you to go beyond and deeper into this to understand why the results are as they are, to explain and analyze from a mathematical perspective, from a data perspective, when you know the data domain, what is happening. Okay, so it's a little bit not quite answering your question, what an example project is. There are plenty of Kaggle data sets that have been studied, but not as thoroughly as we'd like them to be. And so when you take those data sets, some maybe moderately studied, and do some experimentation with them, you can still definitely get an A for that if you have done the requisite analysis. Okay. Another thing that I'll add, I think that is really important that sometimes we overlook, is that we want everyone in your team to contribute. Okay. So in specifically, I'm warning teams that have, very high powered members, and then maybe some stragglers that don't know machine learning well. Okay. Sometimes this means that those individuals take charge of all of the machine learning parts. Okay. Like the parameterization, the optimization, everything, and other people are left out to do the report, the charts, the graphics, the video, etc. Okay, that is not doing justice to this course, right? We want everyone to get their hands dirty. You need to take part in that. Okay, so a good project also has this consideration and will transmit to the staff that everyone has been involved in some part of machine learning for designing the system. Okay, again, you could take it like we've got a bunch of different learners. Each person in the group will be responsible for one learner and one analysis, and we're going to ask through a coordinator in the group, try to pull this all together so we can present it coherently. That is an excellent project. Okay. Some projects are just somehow more fancy or more visually appealing than others, and those typically get featured in steps. And sometimes they have a higher bar of difficulty, but again, that doesn't necessarily correlate with your grade. Okay, so again, if you want to look at some of the projects that are out there, I have recommended a couple from the steps modules. Those are mostly not total beginners, but we do have some samples of ones that are from Kaggle. If I can find from our archives what they are, I will put them up so that you can take a look at what those look like. Okay, all right, so that's good. So we'll hide that one. Okay, so we have a number of other questions. We'll try to go through all of these, okay, in the second half of the Q&A session. So I need to take a water break, pardon me. I'll let you guys enjoy yourselves for a second by letting you annotate. So I'll just give you a screen, okay? And feel free to put up whatever you like on here. It's like, I think you can annotate. Let me just double check. Yeah, so you should. So go ahead and do anything you'd like to the screen except put any, objectionable content. Please don't do that. And I will be right back in 5 minutes. Okay? Okay, we'll get started in a few minutes. Thanks for drawing the cat and playing tic-tac-toe. I'd play with you too. And cool beans. Okay, I didn't know that. Okay, that's interesting to know. Okay, so I'm going to continue for another however much time we need. And so I'll just, again, tell you all, this is an optional session. You're not required to come here. I think studying the past cohort of participants that we've had going through here, the help sessions are actually quite helpful. And, you know, towards the middle of the semester to the end, we have fewer and fewer students coming. And we understand that you guys are very busy. But I hope you come and try to ask questions, and I can try my best to clarify. Again, I don't always know all the answers, and many times I have to go search and correct myself when I make mistakes, and I hope you'll be forgiving of that. But in any case, we will try our best to answer all of your queries. It is extremely difficult given the size of the cohort, and we'll just try our best to make sure that you're happy with your learning experience. So I'll address one of the questions here, well, comments, I guess, that we have on this part over here, which is about this course being hard. Yes, I think if you look at the comments on, NUS mods, this course is not considered an easy course. It's actually also a very difficult course for us to teach because we have mostly school of computing students, and most of our students are pretty good at math, but certainly, we have a different level of mathematics uh, capability coming, and proficiency, I should say, coming from people from the Department of Maths, and in some cases, Faculty of Science. So your expectations will vary, and I will say we try our best to suit the middle ground, which is mostly our own computing students. Okay, so this is why we don't have as many difficult proofs. I mean, the concept learning set of a lecture that we had for week 2 is probably the one that's most involved in terms of math proofs. Okay, but there will be others, right? When we talk about linear regression and how it relates to Gaussian noise, that's another part. As I wrote on one of the forum posts, and again, I definitely highly recommend that you subscribe to the forum, or at least check it out once a week, okay? There's a lot of content that people are putting up, and we're not as timely as addressing all of them, but we would try to get to all of those questions that you put up there. Okay, there's another question that I got a couple times is, the comments that you are making, are they public? If I make a question on the assessment, does everyone see that? And I think the answer to that is no, you shouldn't be able to see anyone else's comment on assessments, right? Those will be going directly to the grader who is going to assign points or give you feedback, sorry, not points, okay? Assign you feedback, okay? When you make questions on the videos, those are public. Everyone will be able to see that. So I know some of you are reticent to ask questions on the videos, and I can understand that, just like 300 other people. But they're very helpful for us, okay? We know our videos are not perfect. They're not terribly good in many cases, and we need your help to continually revamp them. As you can tell, let's say concept learning lectures last week were shot from 2019. I didn't reshoot them because they're not as in bad shape as some of the other content that we have. So we're trying to selectively add new content as well as replace old ones. And that is possible because we're doing flipped classroom, right? We can use the old recordings and we can post edit them and things of that sort to clarify things that are possibly misunderstandings. Okay, so I hope you will continue to contribute, tell us when things are going wrong. We will try our best. Again, no guarantees that we can fix all of those, but I think the course has already remarkably improved from the last time, or the second to last time we've run it. So we are learning. We're also, human learners ourselves, right? In the sense that we're trying to improve the course and learn from that. So a couple of the practices that we have in this course are directly coming from that. right? This idea of having a weekly email, of giving you specific links to within the LMS so that you can go directly to materials without needing to go through everything. I hope those things are appreciated. If not, you can tell us you're wasting your time, Prof. Make your teaching better. You know, don't worry about all these other things. Okay, so definitely we want to pay attention to the overall teaching as well. Okay, so flipped classroom is of course distinctly hard to do, especially for students, because you don't get to interact, okay? So I hope you continue to come back to the help session and make yourselves comfortable with talking to us in small groups in your tutorial. Again, your tutorials, some of you actually have Monday tutorials. Hopefully they were successful. We'll be having a debriefing with our tutorial leaders later in the week to see how it went, okay? So a lot of things have changed about COVID. I think, you know, we have no choice but to lean farther in and try to do a better job of things of this sort. So I hope, you know, I can eventually turn this frowny face into a smiley face, but I'll be honest, this course is not for the faint of heart. It requires a lot of work, quite a bit of math, quite a bit of programming, and a lot of good communication from your teams, okay? And the best way to do it in flipped classroom is, again, engage us, okay? Please do make an effort to talk to us. We may not be able to reply as quick as we'd like to, and certainly not as quick as you'd like us to do, but try, okay? We'll put in our best effort for you, okay? Again, I emphasize that we don't have a choice. There's machine learning is getting more important. It used to be some like small niche specialty, you know, in the 1980s, and so there weren't a lot of people studying this area. But now it's become very, very important because of the amount of data that we have and the amount of automation that we have. Okay, so enough of me spouting nonsense. Let's go back to talk, okay? So thanks for this. I'm gonna take a screen grab. I think a lot of our lecturers have been doing that anyways. So I'm gonna save this, okay? I don't know where it went. Just hope that it's saved somewhere, and we'll go on. Okay, so I'm gonna clear the annotations, obviously, because I won't be able to read anything. And then we'll go ahead. Where's my annotation? Clear all drawings. Okay. So, you know, again, because it's an optional lecture and we've already gone through a lot of these questions, you know, I will stay on to try to answer them. But if you're all okay and you don't have any more questions, don't feel obligated to stay on. You're not going to miss much. You don't have to be kyasu or anything, you know, because we've gone through the lecture, and if you have any more doubts that are not immediately answered by this, you can feel free to ask on the forum or talk with your tutorial staff, okay? That's just, this is meant as a forum for this to be high touch, so we can talk to all of you. Okay, admittedly, it's still a little bit of a broadcast, but it also means that, you know, we don't want to waste your time either. You're already doing lecture, right? You're already doing flipped lecture. You know, ostensibly we have 3 hours of lecture, and so you don't have to use all 3 hours if you don't need to, okay? So, all right, let's get back to the questions. Okay, where is my pointer? Yes, okay. So deriving hypothesis space H from S and G, does H contain the hypothesis in S and G? Okay, yes. The hypothesis set, meaning all of the hypotheses that are representable by a learner, will be the superset, right? It's basically that large box that we saw earlier, okay? So let me see what I can annotate again. Okay, so I have this hypothesis space, okay? Let's call that H, okay? The set of all hypotheses that I can learn given the inductive bias that I have, okay, that I've set, okay? So for example, in a conjunctive learner, this would be the set of hypotheses that are admissible by a conjunctive learning algorithm. Now, somewhere in here, there is a set of things that would be the general and specific ones, right? So we have our general down here, we have specific ones up here, and then we have a version space, possibly empty, that would be in the middle, that represent all the concepts that are in this partial ordering going from multiple G's to a single S, for example. Okay, so H will contain all of the hypotheses in S and G, but it will also contain others, right? Other hypotheses that could have been good hypotheses, but we've ruled them out based on the data that we have observed in the training data, right? This set D, okay? So those other things we've eliminated and we've discarded because they're not consistent with what we've seen in our data, okay? All right. So that one is gone. If version space is the subset of hypotheses that are consistent with D, do we still consider the old S that have been updated in order to count the semantically distinct hypothesis in the version space after running the algorithm? Okay, so when we are saying how large the set of hypotheses are, okay, that you're right, it is sensitive to the time step, right? The amount of data that we've seen, right? The fewer data examples that we have, the more uncertainty in the target concept we have, right? By getting a new example, we are sometimes able to narrow down the set of possibilities, right? So we wouldn't consider the old S, right? The old hypothesis here, okay? Yeah, draw again. Okay, we wouldn't consider the old S, we've discarded, okay? To count the semantically distinct hypothesis when we are considering at that point in time, okay? So there are, I guess, two different questions that are going on here. One is when we ask you to count the number of hypotheses when running the algorithm, okay? And another set, which you saw in the earlier slides, where we were asking you how many hypotheses can be represented. How many different concepts can be represented by this particular learner, right? So when we were looking at the null and the don't care and trying to count all the semantically distinct and syntactically distinct hypotheses, that was a separate question, okay? All right. So this one is done. Okay. Why is it when an unbiased learner, there is a 50-50 chance for it to be positive and negative, okay? So when we look at a version set, okay, and we have a set of, let's say, example, okay? Whatever this instance is, let's say, I don't know, you know, I don't remember what all of the attributes are. Let's say this one is milk. C, O for no sugar, etc. Okay. Then we are considering the label, right? So the label could either be a positive case or a negative case, right? And if we don't have a biased learner, meaning we don't make any a priori assumptions, then the remaining hypotheses out there that could classify it, okay, half of them will have it as positive and half of them will have it as negative, okay? So how do we get that? Again, you recall when we were talking about this case where we had a simple case of x1, x2, and y, right? And we had plus, 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 minus, minus, plus, and minus, minus, okay? And let's say we got some data instances. Let's say, okay, we got a plus here and a minus here, okay? So these two, okay? So this is our x1 and this is our x2, right? The two data instances that we have, okay? Now, we've thrown away some of the hypotheses, okay? But now, let's say we get a new example and we need to classify, okay? So this is our test example. Let's say our test example is x3, okay? And the question is, can I predict what this value is here, right? Okay, so if I have an unbiased learner, well, it could be plus, it could be minus, right? There's a concept where it is plus and a concept where it is minus, right? So one concept that we would have, okay, given these four examples, okay, if I just write it out in a row form would be plus, minus, plus, and minus. Okay, another one, so that would be this one here, this empty spot here, and whatever the fourth one is here, okay? Now, there are other ones, right? So the only thing we fixed at this point is that for this particular concept, these two first values are fixed, right? So I have plus, minus, okay? And then I could fill in anything here. I could put minus, minus. I could have put plus, plus. I could have put minus, plus, right? And so you'll see for all four of these remaining things in this data set, right? Okay, exactly half of them say plus. All right, so let's see, right? So this one says plus, this one says plus, okay? And exactly half of them say minus, right? So this one says minus, and this one says minus, okay? So this is how we say when we're having no assumptions that the space of hypothesis left would exactly have 50-50, right? Because there's no way to know without any assumptions what value it has, right? So when I'm talking about target concepts, I'm saying, you know, for the whole data set here. So out of all the possible concepts here, we only have 4 remaining ones, right? Because we've observed 2 data examples, and we have four items in total. Okay. So great. Let me get that out of the way. Okay. What is the difference between H, P of X, and the size of H, okay? P of X has to do with the probability of a particular occurrence in our data, right? So sometimes we get data and some types of data are more common than others, right? So for example, in Singapore, it's almost always humid, right? So there's the possibility that it's cool and dry, but not very often in Singapore, right? So then we can say that the P of X for some particular examples that we might have to classify are low, okay? So this is what we mean by P of X. So taking that into account is often very important, okay? So when we saw in naive Bayes, we talked about the marginal, which contains this, okay? I'm getting a little ahead of myself because I'm promising to be a help session, so I'm not wanting to go into naive Bayes, okay? But there are certain cases where we want to take the likelihood, the probability of specific data, okay, that we might see and use that as a piece of information to consider, right? H over here, when we're considering the size of H, let me just make this big, okay, is basically the whole idea about how many different hypotheses that I have. Okay, so I think this equation over here is a little bit different than what we normally consider, right? So here in concept learning, we're more concerned about the size of the hypothesis set that we might be looking at. And as we'll see, concept learning doesn't really get us very far. It's very helpful to understand the ideas of learning and the feasibility of learning, but after that, we have to break loose and consider infinitely large hypothesis set, okay? Even something as simple as drawing a simple straight line across you know, a 2D grid has an infinite number of straight lines you can build, right? Because you can have set the intercept anywhere, you can set the slope anywhere, and for that reason alone, we have an infinite version space, right? An infinite hypothesis space. So searching an infinite hypothesis space, you know, at the beginning seems quite intractable because we can't enumerate all the possibilities. But as we'll see, we can still do quite a lot with the fact that we have a very large space or infinitely large spaces to try to find that needle in the haystack called the target function. Okay. When we decide to use an ML algorithm, whatever it is, like naive Bayes or whatever, okay, we choose to use the conjunctive hypothesis. Here, the conjunctive philosophy is the A we mentioned. Yes, okay, I think I know what you mean. I'm saying here that when we are using an algorithm A, right, we're making some a priori assumptions about what type of concept, right? What form the concept has, Okay, so it is related to the hypothesis space, right? When we look at naive Bayes, when we look at KNN, we look at concept learning, like the conjunctive learning algorithm, they all make different ideas of what the target concept should look like, right? So they're going to have some idea of what is representable, right? Anything that they don't think is representable could still be the target concept, okay? But we are just making an assumption that it is reasonable for us to encode the target concept or its approximation as H with a representation of a particular sort, right? So in this first lecture on concept learning, what we're basically saying is we believe that it makes sense to encode the concept of whether a friend likes a drink or any other data set that you have as a conjunction of attribute values, okay, where we allow an attribute to have a specific value, a don't care, meaning anything goes, or not allow any values at all, which is a degenerate case. Okay, so yes, when we talk about here A, we mean basically this script A, right, that we were drawing before, right, the script A, okay, which is basically the choice of the learning algorithm. From this set of all possible learners, I pick an algorithm A, which is the one that you're mentioning here, right? And once I pick that algorithm A, it comes prepackaged with this inductive bias. So on the last couple of slides, we were trying to qualify what is it exactly that we're encoding when we use a particular learner. What form of representation are we saying that the target concept has to fit, or that we're modeling the target concept with in order to reflect the learning? Okay, so yeah, this is a good question. I think hopefully I've interpreted it the way you wanted it to be interpreted. Okay, so let me clean up. Okay, so, okay. What does J test equals expected mean? Okay, well, so this expectation of X, okay, that means basically, as you'll see later, if you don't know what expectation is, that is required information, math concept, but basically it means what's the most likely value of X, okay? And in case you're not really sure what that means, what does he mean, like most likely value? It means from all of the data possibilities, all of the possible rows of X, which ones are most common? All right, like I said, in the Singapore context, let's say we were talking about a weather data set, right? It's not very likely that we would have snowstorms and earthquakes and typhoons in Singapore, but they're plausible. They can be instances in our X, okay? So when we are talking about expected X here, what we mean is for an average or expected data instance, right? So if I take a look at millions of examples of data coming from historical archives of weather, on the average day in Singapore, how likely is it to be classified correctly, okay? So that is what we mean by this J test, okay? It means that how likely is it to draw a particular sample, okay? And then when I draw that sample, how likely is it that I'm going to get it right, okay? So that's what we mean by the error, okay, for our test case, because we don't know which test case we're going to get, right? You don't get to decide. We're trying to estimate how good our learner is, right? Ultimately, we want this to be as low as possible, right? When you go to a client, right, and you say, have I got a deal for you? I'm going to build this machine learner system for you, and it'll only cost you $1 million, okay? And what you want to do is be able to guarantee to that client, I will be able to predict instances from the type of data that you've given me in training, okay, with a certain level of fidelity or accuracy, right? And that basically means this J-test, right? So we want to lower it as much as possible. And all this is different from the training one is because the training, we know what data instances we have, right? In test, we have no idea. But oftentimes we need to estimate it, right? You're not going to go to the bank and say, if you're going to build a credit loan application, well, I don't know how well it will do, but on the data that you gave me, it got this level of accuracy, right? And they don't care what you did on the training data. They want to know how well it does on the test data, right? And so the way that you try to encode this is to say, well, what's the likelihood that different types of applicants will come? You know, an 80-year-old octogenarian looking for $1 million to loan, probably not so likely, right? But, you know, a 25-year-old looking for their first job who wants to get a small loan to improve the look of the resume and do some preparation courses for interviews, that's pretty plausible, right? So it means to be able to get an idea of what the expected X is, right? The average X that we would get and whether or not we're going to do well with it. Okay, so I hope that answers that question. All right, so does the candidate elimination algorithm include inductive bias? Okay, meaning the minimal number of assertions to classify all inputs. I'm not sure I quite understand this question. Yes, it includes an inductive bias, right? When we do candidate elimination, we are again doing this sandwiching between S and G. So it has an inductive bias, and we went over that in the last couple of slides. So I hope that is addressed. Okay. What are the pros and cons of candidate elimination versus find S? Well, basically, we don't use find S, right? We introduced that as a way of thinking about the problem as a first step towards a solution, right? Find S is basically an introduction into a way to do concept learning, but it has some, you know, it has some deficiencies, right? Because it is considering only one hypothesis, right? It's always considering the most specific hypothesis that narrows everything down. Now, there is a pro to it, okay? And that's, if you've taken a lot of computer science courses, you can think about the trade-offs that we have in algorithms, right? So candidate elimination obviously carries a version space. That version space could be very large, right? So that means there's a memory requirement for candidate elimination, right? It has to search over a wider set, it has to maintain that. So the memory requirements for candidate elimination are much higher, right? But it does allow us in candidate elimination a pro of being able to figure out or not whether or not we are getting to a noisy data set, okay? So why is that? Because, you know, our S and G are converging, right? If they get to the point where there's no hypothesis that's left, right? Your S and G has collapsed. That means there's something wrong with your data. Something's not working, okay? And in certain cases in FindS, we actually don't know that, right? I think we saw on the slides, we don't know whether the data is noisy with FindS, okay? So there are all of these pros and cons. So actually, even though this was voted down, this is not a bad question, okay? So hopefully that one is done. Could you present another example using candidate elimination algorithm? We could. You might see some on your tutorial. You might see some in your midterm. Okay, so there's when I'm going to present another example. If you're not sure and you want another example constructed, you might ask again on the forum or ask the TA. And if we have bandwidth, we can consider it. Unfortunately, because there's enough other things to fix in the course, we may not get to all of these, you know, nice to haves, but not essential. Okay. We assume that the target concept can be represented as a conjunction of constraints, right? And yes, we do. When we are saying we are using a conjunctive learning algorithm, okay, we can classify unseen input instances, but the confidence to do so may vary, okay? So for the purposes of proving, right, we said that in candidate elimination, okay, we don't actually classify instances that have conflict, right? So if the version space has a number of hypotheses and those hypotheses don't agree on whether that instance is a positive or negative, we're just going to ask our candidate elimination algorithm and say nothing, shh, don't tell anyone, okay? Because for the purposes of the proof, okay? But in reality, again, like I said, every learner out there, you would be crazy if you ask the learner to classify things and it just says, I'm not going to tell you, right? So many times what we do is we make this assumption that all of the hypotheses that are inside of the version space are equally plausible, okay? So that means we assign each of those hypotheses, like say when we draw that thing again, okay, let's see. Okay, when we draw, let's say we have two general hypotheses, one specific hypothesis, and three other hypotheses. We're going to assign each of these, a 1/6 probability of being the target instance, right? Then it's very easy. We can say, okay, I'm just going to take your possibility of being the correct target instance times what your vote is. I'm going to add them all up and I'm going to take a vote, right? So if I have, let's say, these four all voting yes and these two voting no, then I would be able to calculate the probability and then declare it as a positive instance with some level of probability, right? Now, again, this makes a difference that we are considering it as uniform probability here, right? If we are not saying it's uniform, okay, we say maybe some of these data instance hypotheses are more likely than others, okay, for whatever reason, if we have auxiliary information for that, then we might not use this uniform distribution, right? We could say some of these hypotheses are more likely than others, right? We may say, oh, the ones that are very specific and less likely, the ones that are more general, more likely, for example, okay? And then we could change or permute the level of uncertainty or the level of confidence, I should say, attached with each hypothesis being the actual target function. Okay, great. All right, the last question. Okay, for lecture video, is the notebook available? Yes, actually, you have this, I think, in the actual case for this. So if you don't have this, you can let us know. I think it is actually worked in the actual examples for the videos for the pre-part of the lecture. Okay. So if you have any questions, again, you can let us know. I think, yeah, the notebook, it should be in the version that you got today. So just be careful though. All right, the version that we have has to be the version for this semester. Okay, so if you go to the previous links for notebooks, you will get the wrong one, okay? So there was a post on the forum to say that the link that we gave you was the wrong one. So you need to make sure that you're using the right link. All the links this year look like something like this, O3 collab.html. Okay, so it has to have this suffix because SOC changed the way files are handled. They put in a different file handler. So we have to have the HTML suffix for the redirects to work, okay? So you know what the other half is. It's basically this part that has our web server COMP in it, okay? And then as I released to you guys through email today, we have built a short link system, which our TAs are busy trying to implement, which is that you only need to change this number in order to get to subsequent notebooks. But we ask you to only use those links when they are supposed to be ready, because sometimes we will release information for our own internal review. If you do those will be fine. They may not be the exact same ones as at the end, so you may have a slight differences. Okay, so please go look at the notebook. If we don't have this particular segment from this, we do have the previous notebooks. You can let us know in the forum, and we'll make those available to you if you'd like to study those. That's no problem. Okay, great. So, okay, ladies and gentlemen, we are actually done with our help session. It's 5:30, so we're going to end lecture a little early today. And I so hope you have an enjoyable tutorial session this week, and stay tuned. Again, when you do your coursemology, by default, all the text entries that you have to do will be auto-graded as correct, okay? What we want to do for counting coursemology grades, okay, is just to make sure that you're keeping up with the work, okay? So we want you to do the notebooks, to practice the programming, to practice understanding the concepts in a hands-on manner rather than just through lecture and self-study, okay? But they're not graded punitively, okay? They're just going to give you formative assessment, meaning that whatever feedback you get from your tutorial leaders will give you a positive or negative feedback about whether you got the answer right. But in coursemology itself, when you submit the assessment, it will just simply mostly say correct, okay? The prompts that we're giving you back to give you feedback hopefully will be a little bit indicative of the feedback that the tutorial leaders will give you as well, okay? So with that, I'm happy to conclude today's help session. So I wish you happy learning, and I will see you all next week. Okay? Cheers.